might be like the cool down for your brain, where you just get to take it easy a little bit at the end of the marathon. I'm going to talk about geometric T-dualization, by which I mean some geometric way of implementing T-duality, what T-duality does to a given space-time. My name is Calder Daenzer, and I'm from Penn State. So T-duality is like, I give a lot of talks on T-duality in various contexts, and it's hard to describe it because it has a different meaning depending on what kind of mathematician or physicist you are. So T-duality has different meanings or different definitions in what? In physics, in differential geometry, in topology, algebraic geometry, algebraic geometry. And what they are, well, I think everyone knows in physics that it's supposed to be an isomorphism of string theories, and it's on two different spacetimes, though, where you obtain one by taking a circular direction in one spacetime and inverting its radius. Or you can do it with, you can do it with one circle or with many circles, an n-torus. And that's the physics version. In differential geometry, they have, they can have a principal torus bundle and try to find the T-dual of that. So there's some global topology there. And then they carry along generalized geometric structures, which encodes the Busher rules, essentially. Encodes a metric and B field and stuff like that. And in topology, it's a little different. Really, all they care about is K theory of a given space-time, which is something coming from physics. But again, they'll have a principal torus bundle, and then they'll have a gerb on it. And the gerb is something which is corresponding to the Navier-Schwarz 3 form that you have in physics, the dB, if B is the background B field. So, and then finally in algebraic geometry, it's again totally different. You'd have some elliptic fibration, say, and you're trying to get a T-dual of that, which should implement an isomorphism of derived categories between a space and its dual. And in that case, they think of the dual torus not as something with inverted radius, but they think of it as like the dual torus is pick 0 of the torus, or it's the moduli space of flat line bundles on the torus. So many different definitions, and I'm going to just try to say that, well, first, I'll say everyone agrees, I think, that the dual of a torus, if T is just given as, it's a vector space modulo a full rank lattice, so that's something homeomorphic to Rn mod Zn, then the T-dual is going to be hom from this defining lattice into the circle group U1. Unitary operators on one-dimensional vector space, if you want. And this is, again, a torus. And this happens to be the fundamental group, so this is the representations of the fundamental group, irreducible representations of the fundamental group, which is how you get the connection in algebraic geometry, that it's parametrizing flat line bundles. So that's T-dual for a single torus. And now I want to describe extend this to give an operation to an operation that produces a dual, the underlying dual geometric space of a principal, or I'll just say of a torus bundle with gerb. If you don't know gerbs, then you get annoyed that people in T-duality always talk about gerbs, but they're necessary because if you take the T-dual of a torus bundle without gerb, it's going to have a gerb on the other side anyway. So it's not something that you can just ignore. And the method is I'm going to use abelian group stacks, which are actually easier than regular stacks. Easier to describe than regular stacks. Easy because of this dictionary of Deline's. And it's the following. If you have just a homomorphism of abelian groups, let's say these are topological abelian groups, G and H, and I don't even have to name the homomorphism. I'm just going to call this a short chain complex. Really short, it has length 2. Short chain complex. And, well, that data gives you a groupoid. It's the transformation groupoid for G acting on H via this homomorphism. If you have a homomorphism of groups, then this guy acts on here. You can make the transformation groupoid. And this groupoid itself has an addition. This is the space of arrows, and it is G cross H as a set. And so it has the group law of G and H gives us a multiplication, which is functorial. So this is actually an abelian group in groupoids. Such a thing would be called a Picard groupoid often. So these data are equivalent. You can go back and forth. And you can also go back and forth from this to this abelian group stack, which I guess the notation I'll use is just kind of a bracket H stack equotient by G. That's abelian, strict abelian group stack. And so in this picture, H corresponds to spatial directions, and G is the stacky part. Right? So if this was nothing, then this would be a point modulo G. That's the trivial G gerb. And if G was nothing, then this thing would just be equal to the space H. But we're remembering that it's a group also. So it's more than just thinking of it as a. You remember that this thing as a stack is a group, also a group object in stacks. Okay, so these have a notion of Pontryagin duality. I already said that. Well, the notation for this operation, when you take hom blank into U1, I'll call it lambda hat. So the hat denotes Pontryagin dual, taking the homs into U1. Well, there's a Pontryagin. Well, let me first say one more thing about this. This is an equivalence of two categories, sort of. You have, if you had a homomorphism of short chain complex, a morphism of short chain complexes, that's the same data as a functor between two of these guys. And that's the same thing as a morphism, an additive morphism of group stacks. And if you have a degree -1, let's just put some degrees for fun in here. So this sits in -1 and 0. And then like if you had a degree -1 morphism, that would be like a chain homotopy. That'll correspond to a natural isomorphism here. And that'll correspond to an automorphism of between two functors there, or between two morphisms. And what about Merida equivalence, right? These guys are really supposed to be corresponding to Merida equivalence. Well, it turns out that a quasi-isomorphism here is the equivalence here and is the Merida equivalence here. So you think of these short chain complexes up to quasi-isomorphism is the same as thinking about group stacks. All right, and so they have a Pontryagin duality. Really simple to define. If you have one of these short chain complexes, I want to define the Pontryagin dual of this, but I'm going to define it here for ease. And I just send it to the Pontryagin dual, which is going to be hom dot of G to H into U1 to 0. So these are chain morphisms. If you think of the degree 0 chain morphisms, well, they can just be homomorphisms from G to U1. And then there's the degree -1 chain morphisms, which are just going to be homomorphisms from H to U1. So it turns out, if you just check on your notepad, this is the same thing as the Pontryagin dual of, it's the homs from H into U1 and the homs from G into U1. And if this was a map phi, then this is just the map of precomposing with phi. So I'll call it phi upper star. So it's a super simple thing, but it does have to be a theorem that this is well defined at stack level. Well defined for stacks. And it's a duality if G and H are locally compact Hausdorff spaces. So you can define it for any topological groups, but when is Pontryagin duality something that you do it twice and you get back to where you started? G hat hat equals G. That's when your groups are locally compact Hausdorff. So, and well defined for stacks means that if you had a quasi-isomorphism on this side, if two of these are quasi-isomorphic, then their duals are also quasi-isomorphic. So that would make it well defined for stacks. Let's see what do I write next. So a couple remarks about that are, let me check the time. 25 minutes can go really fast. I have, okay, 18 minutes left, I guess. Okay, so remark is that this works for bundles of group stacks too. So let me see how I want to say it. So this extends Pontryagin duality extends to locally trivial bundles with fiber being H mod G. So if you have locally trivial group bundles that are locally isomorphic to this cross some space, then you can also apply Pontryagin duality for those. And the reason is just essentially from functoriality, because if you imagine at the level of the short chain complexes, say you're going to be taking some space, some small set U, so it's just topological space U, and well, let's say local triviality means that you need to have something which is locally isomorphic to this, and then on double intersections you would want to have some kind of gluing transition functions. Well, what are they going to be? They're going to be chain morphisms like that. If you call them rho, then what's the effect of doing Pontryagin duality? It's going to give you H hat to G hat cross U. It's going to give you another set of transition functions. So basically, to say it in one sentence, if you have transition functions defining some locally trivial bundle of short chain complexes, then taking Pontryagin duality, you're going to get dual transition functions, which also work out. And similarly, and also if you had a homotopy, that would also dualize to a homotopy. Oops. So you can apply it to bundles. What's another remark I want to make? Well, another thing just to note that's interesting is that it interchanges the spatial parts with the stacky parts. So if you take something that's all space, and then you apply the Pontryagin dual, you're going to get something which is all stack. Now let's use this to make that's all the theory, I guess, that we need, and now we can just make this operation that gives you T-duality. First, I'm going to redo this operation just for a single torus, where you go from T to ohms from T into U1. So T to T dual using group stacks. The operation might look a little funny, but here's what you do. You take T, it happens to be a group, but you can view it as a group stack or a short chain complex that has only a spatial part. Next, I'm going to take a stacky quotient by V. Remember, T is vector space V modulo full rank lattice lambda. So I'm going to mod out by V, and all that amounts to is taking the inclusion of chain complexes from 0T into this guy, right? Because this one represents the stacky quotient of T by V. And now I'm going to do Pontryagin duality. So this is a quotient map. It's an actual morphism. And then Pontryagin duality. That's going to give me T hat to V hat. And I claim that this thing is actually quasi-isomorphic to the, well, it's clearly quasi-isomorphic to 0 to V hat modulo T hat. And this is also just equal to lambda hat. That's just a fact. So it's equal to the dual torus. This is a Q-iso. OK, you could have done it another way. You could also note that there's an inclusion of chain complexes like this, which is a quasi-isomorphism, because this is a surjective map, and its kernel is lambda, right? This is just V mod lambda. So that's a quasi-isomorphism of two-term chain complexes. Therefore, it corresponds to an isomorphism of group stacks. So I can replace this guy by this, and then do the Pontryagin duality. And what am I going to get? I'm going to get 0 to lambda hat, which we already said this thing is T dual. So that's another, you can go any route you want. You're always going to get T dual. Now, are there any questions? OK, now I'm going to extend to the bundles. So if you have a principal bundle, the first thing to note is that a principal torus bundle is not a bundle of groups. So now extend to some principal T bundle over a base space M. And I'm going to, since this is the warm down for the day, I'm not going to include the gerb, though we'll get one on the other side. This guy's not a bundle of groups. You cannot, if you have two local sections of this, you cannot multiply them, right? On the other hand, so P is not a bundle of groups, so you're not going to be able to do any Pontryagin dual, because you can't say what is a homomorphism from this thing into U1 if it's not a group itself, right? So P is not a bundle of groups, but if you take this other guy that I'll just call script P, I guess, which is the disjoint union of all the powers of P, that is a bundle of groups. What does this mean, the powers? Well, if this principal bundle is given by some given transition functions, then P squared should have the square of the transition functions, and P cubed should have the cube of the transition functions. That's something you can only do for a principal bundle whose fiber is abelian. Right? So that thing is a bundle of groups. So the short answer, is that the dual of this guy is just, you start with P, you do the stacky quotient. So let me write this. So this is really, let me go back here. This is just T dual is take T, apply the stacky quotient, and then do the Pontryagin dual. That's what I wrote out sort of in longhand. Right? First we did stacky quotient by V, then we did Pontryagin duality, and then we noticed it looked like something familiar. So you can do the same thing here. You could do P mod V. Now this is again a bundle of groups, and now we'll take its Pontryagin dual, because I said that a bundle of groups can be, or a bundle of I guess, short chain complexes can be dualized. And that is the answer. Of course, this is not very understandable. So now to finish off, I'm going to explain how this works in more detail. But that's what you can take home and say, oh, I know what Pontryagin duality is. It's this operation where you mod out V, or it's at least one way to present T-duality is you mod out V and then take a Pontryagin dual. So
is it clear what the non-scripty P is supposed to go to?
Yes. Well, it's a good question. This thing is, in fact, a U1 gerb over a trivial dual torus bundle. And you notice that if you ever looked in the algebraic geometry literature where they're talking about equivalence of derived categories, they talk about this degree 1 piece of the derived category that corresponds to some sort of chunk of the gerb. And that's the image of P, would be that chunk of the gerb. And I think it will be obvious once I write out the details. OK, so more details. So we have P over M. And suppose we have some cover over which it's trivial. So you have some guys U alpha, and P restricted to U alpha is trivial. And you have transition functions going phi. Suppose so U alpha intersect U beta goes to T. And I'll just call this map rho. These are transition functions for P, then I claim that I'll tell you what the transition functions are for script P. U alpha intersect U beta will go to, well, it's going to go to the automorphisms of T cross Z. Sort of what you expect. You expect script P. If you think of it as some object living over M, it should have fiber equal to Z cross T. And it's just, again, it's something that I'll call it chi and chi rho, I guess. Chi sub rho applied to a point T, comma N is going to be rho to the N times T times N. It's kind of funny the first time you see this, but this is actually a group homomorphism. If you took, so here's the Tn, and you took a T prime, N prime, and multiplied them together, and then applied chi rho of it, that would be the same as first applying chi rho to each one and then multiplying. It's homomorphism. Funny looking one maybe, but, and I'm omitting the point, it should be rho of some point U in there, but I'm just going to omit it. And here you see the nth power thing, so that this thing is actually and that is a transition function presentation of script P. Another way to, let's see. Let's go back over to this board now. Next. Okay. So P, script P is locally something that you could write if you wanted to write it as two-term chain complexes. It's locally T cross Z. And then it has transition functions chi rho. Like that. So now what's P mod V? Now it's going to be easier to see what P mod V should be. And P stack equotient by V then is locally of the form V going to, let me write it over here, V going to T cross Z. And it has transition functions that are just going to be the identity on the V component And this map, by the way, is just sending v to t comma 0. That's what this map is. Still the chi-rho here. So that's what p mod v, that gives you a local presentation of script p mod v. And then the Pontryagin dual, so p modulo v hat is locally of the form, well, t hat cross z hat. I'm just taking the Pontryagin dual of that, going to v hat. And that's the same thing as t hat cross u1. Z hat is u1, right? Going to, and v hat is just the dual vector space, if you want. And then it has transition functions, the trannies. This is on video, oh boy. Cross u1. Okay, what are they? They're just chi-rho upper star. And this is just the upper star of the identity map, so it's, again, the identity. And then just check out what this is. And once we check out what this is, then I'm going to have given you an explicit description. Given the transition functions defining P, then give you transition functions defining the dual as a gerb. Okay, so chi-rho upper star of, so this is just a quick calculation or claim, chi-rho upper star, if you're going to apply it to a point lambda and a point z, I claim that it's just lambda comma z and lambda paired with rho. Rho is a transition function that's valued in t, and lambda is a point of t hat. So you can evaluate them, and you get an element of u1, and then you just multiply it. So how do you check that? Indeed, chi sub rho of lambda comma z, if you were to apply it to a point in the torus and an integer, that's the same thing. It's supposed to be precomposing, right? So it should be lambda z applied to chi-rho of Tn, which is lambda z applied to rho to the n times t comma n, which we saw before. And what is this? This is just evaluating things. So that's lambda evaluated at rho to the n times t and z to the n. This is supposed to be a point in u1 by evaluating this function that's valued in u1 on this point. Right? And that's the same thing as lambda of t times z lambda of rho to the n, which is what you get if you apply this thing to this point. Right? Okay, so that's how you check it. And what does that leave me with? Well, I think that's all I want to say in terms of calculations. Oh, except for that there's an obvious map from this guy. Let's see, where am I here? There's an obvious map from here where you kill off u1. And if you kill off u1, since chi-rho only does something to the u1 part, so if you kill off u1, you get nothing but a trivial t hat to v star. And remember, t hat to v star is quasi-isomorphic to the dual torus. The v star mod t hat is the dual torus. Right? So if you kill off u1, you get a trivial thing. So this thing is something which lives over a trivial torus bundle. And it's a non-trivial u1 gerb on a trivial torus bundle. So that's one way to construct it. And similar thing, once it's kind of funny the first time you see it, I have to admit, but this operation is easy to remember. And anyway, that's that. But the upshot is So, okay, it's not just a redo of stuff that everybody that could be done in other ways. It does have some actual benefits, and I'll just mention them, and then I'll be done. So, the upshots is that we just used, the only thing that we used to make this construction work was this inclusion of T into the automorphisms of T cross Z, where you send, which is just chi, where you send a point T to the automorphism that sends T prime n to T to the n times T prime times n. That's what chi is. And we just applied that to the transition functions of a principal bundle, and that's what made the whole thing work. So it should also work for other things that you can map into aught T cross C. So this also works for the affine group of the torus, which I will remind you is the group which is the semi-direct product of T and automorphisms of T, which automorphisms of T are just GL of lambda, or GLNZ if you like, and T is the translation. So this is a bigger group than T, and what you call something an affine torus bundle if this is its structure group, right? So an affine torus bundle is worse than a torus bundle. It has less, because it has a bigger structure group. Well, this thing also goes into aught T cross Z, where you send T in. If you had a point T and an element of GLN of lambda or GLNZ, you're just going to send them to chi of T composed with A comma the identity on Z, which is an automorphism of T cross Z. And so this allows you to calculate directly the T-dual of an affine torus bundle, which is of interest to mirror symmetry people because in the Calabi-Yau threefold, you're going to have an affine torus fibration, not a principal torus bundle. You have an affine torus fibration, and you want to know, how do I T-dualize that? Well, you can do this to an affine torus bundle. So that, I think, has not been done before, although David Baraglia 2 years ago at this string math conference proved, abstractly that you can find T-duals or that T-duals exist to affine torus bundles. So that's the upshot. How am I on time? Am I done with time? I think I'm over time. OK. Well, anyway, this operation, being as algebraic as it is, it works in algebraic geometry and topology, whatever. I mean, you can replace by Cartier dual if you're replace Pontryagin dual by Cartier dual if you're an algebraic geometer. Thank you for listening.
So, I mean, usually in T-duality, like as you said at the beginning, there's like the relationship between some group or category associated to one side of T-duality, whether it's the K-theory in topological T-duality or the direct category of coherent sheaves. So what's the sort of invariance of one that's related to the invariant to the other?
Well, the thing that you get automatically in this setup is a Poincare line bundle, which can be used always. If you have P and you have P dual, then I claim that there's always going to be a line bundle on them that you can use to make a Fourier-Mukai transform from D of P to D of P dual if you're in algebraic geometry, or you can find a connection on it and use that to do the differential geometric version. If you want to translate it into differential geometry, you just choose a connection on these guys, and that gives you an Naval-Schwarz 3 form, and this choose a connection on here. That gives you the differential geometric version. So I think that sort of any of them can have it. And a really cool thing about this Poincare line bundle is that it's something that you have on any two group. If you have G to H and you have its dual, there's a canonical evaluation map to U1, and there's a canonical line bundle on on u1 to 0, right? It's just the complex numbers acted by multiplication. And you pull it back to here via the evaluation map, and that gives you the Poincare sheaf. So you don't even have to make any choices at all. So yeah, that's my answer.
There are no other questions. Let's thank